Let's talk plate tectonics. To explain plate tectonics, we have to begin with processes that are in the interior of the Earth. And that begins with differentiation in the creation of a layered Earth. In the beginning, the Earth came together and it was a mishmash of atoms of different sizes and different compounds. That Earth melted, and when it did, the heavier elements sunk down to the center of the Earth, and the lighter elements migrated to the outside of the Earth, giving us differentiation. The layering then is the core, the mantle, and the crust, and that is based on composition. In the interior, in the core, we have an iron nickel core. In the mantle, we have silicate minerals and iron and magnesium. And then when we get to the crust, we're mostly dealing with silicate minerals, those less dense atoms. So how do we know about the interior of the Earth? One way is by looking at seismometer readings. This is a seismograph. So this is a graph that shows the P wave, the first wave to arrive when they're shaking from an earthquake. The second wave is the S wave. Those are waves of the interior, and then we have the surface waves that create the shaking at the surface. These waves are going to travel through Earth's material at different speeds relative to the density of those layers. So earthquakes wave revealed Earth's structure. We can look at the arrival time of seismic waves and think about then the chemistry, the density, and the physical state of those layers. Okay, the type of seismic waves here. So there are body waves and surface waves. The P and the S waves are those body waves that are in the interior of the Earth. The P waves is a wave of pressure. So A up here is the P wave, a compressional wave. It's the fastest, it's the first to arrive. And those P waves and compression waves can go through solids, liquids, and gases. The next wave is an S wave. It's a little slower than the P wave. It arrives later. It's a wave of shear motion. So imagine a whipping of a tail here. And it is only going to go through solids. We can't, or waves don't shear liquids and continue to propagate that wave, and waves don't shear gases and propagate that wave. What that gives us is earthquake shadow zones. I'm going to turn off my face. So an earthquake shadow zone means that if an earthquake occurs, so the top of the globe here, the earthquake is occurring. If the Earth were just one solid ball with a consistent, homogeneous physical state and what it was made out of, the waves would just travel right through it. But it's not the case. The waves, and A is the P waves. Excuse me, A is the example of if we had just a homogeneous globe. What we see in P in figure C and figure D is what the waves look like for real. So the first one on the left is the P wave. And the P wave, it can be transmitted through the liquid outer core, but it gets deflected, and this deflection then creates these green areas on either side, and that is the shadow zone where there's no P wave detected. The waves can go through the liquid though, and they come out the other side. There's just these shadow zones where that refraction occurs. On the other one, figure D, these are the S waves, and the S waves literally stops at the outside edge of the liquid outer core. So the S-wave shadow zone is pretty much the whole other side of the globe. All right, so we can look at the Earth and we think about the layering in two different models, is what we call it. One model is that we have a crust, mantle, core, and those are mineralogical differences which come about because of chemical composition. The other model, and this was developed along with the theory of plate tectonics, is not only are there mineralogical differences, but the different layers have different strengths. We have weak layers and strong layers. The two models work together. They're complementary, not contradictory. We just have two ways of looking at the layering. So in model one, I'll turn my face back on. Whoop. In model one here, this is a crust, mantle, core. The rocks on the outside or from the crust have a lower density. They're lighter colored rocks. The average composition of the continental crust is that of a granite. The oceanic crust is all basalt. The mantle is darker colored, heavier, denser rocks made up of olivine, and it is just denser, heavier, darker colored rock. And then the core is the iron nickel core. So model 2, my face again, we've got a little bit more going on here. This is based on the strength of the material. So in this image we have the hydrosphere, that's just the liquid outer layer, the lightest of the elements. Well, the atmospheric gases would be the lightest. And then the hydrosphere. Beneath that is the lithosphere. Beneath the lithosphere is and that is solid. Beneath that is the asthenosphere. And beneath that is what we call the mesosphere. And then we go to the outer core, which is liquid, and the inner core, which is solid. So let's bump back up here to the lithosphere. So the lithosphere takes in the crust and a little bit of the upper mantle. The asthenosphere is beneath the lithosphere, and it is a soft plastic. It can flow, but it's not liquid. And then the mesosphere is a stiffer plastic. All right, so this just summarizes some of those different layers here from model number 1 with the crust. There are two different kinds of crust, continental and oceanic. And then there is the mantle and the core. This gives you the depth range and the thickness. The crust ranges in thickness from, the continental crust is an average of 40 kilometers. The crust underneath the continents can get quite thick underneath mountains. And then the thinner oceanic crust is just that crust under our ocean basins. The composition for the continents is that of like a granite, and then the oceanic is that of like the rock type basalt, igneous rock, kind of equivalents to the composition. Okay, the mantle also has silicates in it, but they are very much iron and magnesium rich. Like I used the word olivine earlier, and the core is the iron nickel. Let's switch over to model number 2, where we're looking at the physical properties. So we have the lithosphere is solid. It behaves like a brittle solid. So if you crack it, it's going to crack. If you bend it, it's going to crack. The asthenosphere is solid, but it can flow. We can bend it. It's not we, but Earth processes can bend the asthenosphere. The mesosphere is also a solid. The outer core is liquid, and the inner core is solid. All right, the lithosphere, again, is the crust and the very much of the a little bit of the upper mantle. They are fused to each other. Between the two, I didn't go here, but is the moho. The moho is a layer that is, or a surface, a boundary that is detected by those earthquake, um, the seismic waves. We can see that they bounce off the moho. Okay, here's the moho. The asthenosphere is underneath, on here it's way down here, is the asthenosphere is the weak and behaves ductily. So if pressure is put on it, it's going to yield to that pressure. Isostasy is a term that we use to talk about the layers of the earth and how they are, the elevation of them can be high and the elevation can be low, and if they have a root to them. So I mentioned before that underneath the mountain chains, there's a really big root to that crust, and that is going to hover kind of along a line of equilibrium, in that the crust is just thicker underneath the mountain chains. Here's the look at what I was talking about. So if you take a piece of wood and you float it in water, the water is going to be displaced by that wood and it's going to float up above the water. That is similar to what happens with the continents in floating kind of above the mantle. They have that huge root below them. Like the Himalayas, they have this big thick section that goes down into the mantle. Let's talk about plate tectonics then, and we'll talk about Alfred Wegener. He was a man that came up with the beginning ideas of plate tectonics, and we'll call that continental drift. Okay, so in continental drift, Alfred Wegener, he was a German, and he was a meteorologist, an astronomer, an Arctic explorer, and a champion of continental drift until his death in 1930. What continental drift was all about is that the continents are not fixed. They move about the globe. There are large-scale movements of continents around the globe. And if you were given continents and asked to fit them together like a puzzle, you two could fit them together. There's a little bit of overlap and a little bit of gap in there, but we can look at a globe and see that if you squish all the continents together, they would fit together like a puzzle. Alfred Wegener looked at many different lines of evidence. He looked at that puzzle and the fitting together of the continents. We call that Pangaea. He and other scientists looked at these very unique fossils that he could trace across continents. Plants from Australia that he could place in Antarctica and all the way across Africa and India and down into South America. These organisms, different ones from different time periods that he could trace the fossils across continents. There also are mountain belts that have similar age. They can do isotopic dating and match mountain belts across. Here's North America, Europe, and Greenland. And then so fossil evidence, and then mountain belts, and then the sea there is different rock units that are unique on these coastlines of South America and Africa. And they have the same ages and similar composition. And then another neat one is areas of glaciation. So centered around Antarctica, there were glaciers, and coming off of that as well, they can look at glacial movement and map glacial activity that all maps together around Antarctica with those continents. All right. So Pangaea was the supercontinent that fit together with the puzzle, and it split into Laurasia and Gondwana, and then continued. Our ocean basins expand, and that has the continent configuration that we have today. The books that were published, he published The Origin of Continents and Oceans in 1912 and had these sketches. Alexander du Toit, he in 1937 expanded on that. And look at the name here, Our Wandering Continents. So it really was about the continents moving around the earth What was lacking here was a mechanism for how that happens. Had all the evidence, but no process. So Alfred Wegener's observations are still true today. We still have the fossil evidence, the glacial evidence, the rock evidence, the mountain belt evidence. But in the early 1900s, geologists didn't believe him because he couldn't explain how the continents could plow through the ocean basins, how they plowed through the crust. One idea was maybe they were swung into place by the Earth's rotation. So we'll look at some of that evidence.